Hello, everyone. I'm Navneet from Google. I'm going to talk to you about Glean, a system we developed for performing structured information extraction from templatic documents. Lots of business processes deal with templatic documents. These are machine-generated documents created by filling out some kind of form or template. Think of invoices, receipts, bank statements, tax forms, and so on. Businesses often receive such documents from their vendors and from customers, and they often have to manually extract the key pieces of information from these documents into their internal systems for further processing. This task is often tedious and manual, error-prone, and if you can automate it away, that'll have a huge impact on the efficiency of lots of businesses. So let's formalize this problem a little bit. Let's pick out a document type, let's say invoices. There's a schema associated with that, and that consists of some fields and corresponding types. So an invoice date is a date, a total amount is a price, and so on. We also have a set of label documents where some human has manually annotated all the invoice dates, total amounts, and so on. Our task is to learn to extract from unseen documents. Now, invoices from different vendors can have very different layouts. Even if they have the same contents, they may be laid out in very different ways. So our task here is to extract not only from unseen documents of the same templates, but even from templates that we have never seen before. This problem is actually quite challenging because it straddles both natural language processing and computer vision. The fact that this date over here is the invoice date for this document is clear to us only because we see that these words here are on the same line. But in this document, it's because this date is aligned vertically with this word date. In layout-heavy documents like this, visual cues like this are very important in understanding what to extract. There are only short text fragments for the word, unlike traditional NLP problems where we have full sentences. So we really need to develop entirely new techniques to correctly extract from such documents. Then that's exactly what Glean does. We begin with a document image. This could be a PDF file or a scanned document. We perform OCR to extract all the text in this document along with their bounding box positions. We also perform named entity recognition using an off-the-shelf library or service to identify all the dates, addresses, prices, and so on. We combine these annotations with the type information in the field schema to generate candidates. Knowing that an invoice date is a date, we can say that only the dates in this document are candidates for extraction. We then score all these candidates independent of each other using a scorer model, a machine learning model that we're going to discuss later. And then we pick out the highest scoring candidate for each document, for each field, as the extraction result. This is the overall system architecture. The crux of the problem really is how to do this scoring correctly. So let's look into that a little more. In the scoring problem, we're given a candidate and a field, and we ask ourselves, how likely is it that this candidate is the extraction value for this field in this document? Now, that determination must be made based on what words are in the neighborhood of that candidate. In fact, the value of the candidate itself isn't very important. Almost all dates are about as equally likely as each other to be the invoice date. It's really the words in the neighborhood that tell us that this must be the invoice date rather than the delivery date or the due date. So our key idea here is to use a deep neural network to learn a dense representation of the candidate neighborhood, and then we can use a classifier to determine whether this is likely to be the actual extraction value for this field. And that's what the novel architecture that we developed does. This is an architecture that's transformer-like. It uses self-attention similar to all the NLP models in literature today. The details of this work are presented in this ACL 2020 paper, but we won't discuss that today. Overall, the system performs remarkably well. In fact, for most fields in the invoice domain, we actually exceed the 80% goal that we set for ourselves. And some of them, we actually exceed even 95% F1 score. For smaller document corpora, like insurance statements and pay stubs, we're able to perform very well just by using transfer learning from invoices. Now let's switch gears a little bit and talk about a key insight that we have learned from working on this problem. Our experience tells us that design choices in training data management can have a significant impact on the overall system performance. In fact, this can be sometimes even more important than ML modeling choices. To back that up, let's look at the training data flow in Glean. So this is how we train a scorer in Glean. We start with a document that has annotations from the NER annotator. We generate all the candidates. In this case, all the dates become invoice date candidates. We also have the ground truth that somebody has manually annotated, telling us that this particular date over here is the invoice date for this document. Next, we label each candidate by matching it against the ground truth. We also pick out a model architecture, let's say the transformer-like architecture we just talked about, and a training procedure then gives us the scorer. Much of the literature on this subject and many others is really focused on this ML modeling architecture choices at the bottom of this slide. What if we use a simpler ML model? What if we use an off-the-shelf multi-layer perceptron rather than this custom-made transformer-like architecture? It turns out that that would have a 1.4 F1 drop in performance. And that's quite significant in the context of this problem. But there are lots of other choices that we made in the design of this training data flow that aren't discussed in literature quite as often. For example, what set of labeled candidates do we provide as training data for the model? In particular, suppose we have a document where there's ground truth available, but there are no candidates that match that ground truth. Here's an example invoice where the due date is just upon receipt. Those are not words that the NER annotator recognizes as a date. In Glean, we throw away the candidates for this field and document from our training data. But what if we actually included such candidates too? It turns out that that would have a 2.3 F1 point drop in performance. That's significantly larger than switching to a simpler model architecture. Let me take one more example. Given a candidate and some ground truth, how do we label that candidate as being positive or negative? In Glean, we do this by saying that a candidate is positive if it has substantial spatial overlap with some ground truth. But what if we were to use the text of this candidate instead and match the value of the ground truth with the value of the candidate? These two matching functions can have very different behavior. In this invoice right here, the total amount at the bottom of the page actually matches the invoice amount, the line item amount right here. Now, even though these two have the same value, this amount here is not the total amount. And if we were to label this as a positive and provide that as training data to the model may actually learn to extract the first line item in every invoice rather than the total amount. And that would obviously be wrong for invoices that have multiple line items. That's exactly what we see. Using matching by value rather than matching by position actually leads to a 2.4 F1 point drop in performance. And that's significantly bigger than the other things that we talked about. In the paper, we also discuss a few other examples where training data management choices, like what candidates to keep, have a huge impact on the overall performance of the system. So our takeaway from this is that design choices in training data management have a huge impact on performance, in fact, larger than ML modeling choices sometimes. In Glean, we've developed a suite of tooling for understanding, measuring, and debugging performance at every stage of this pipeline, precisely for this reason. We think that this is an avenue for fruitful future research in this data management community. Thank you.